Everything around us is made of matter, but physics tells us that many particles have an opposite partner, antimatter. An electron has a positron, a proton has an antiproton. The idea was predicted in 1928 by physicist Paul Dirac. Then in 1932, the first antiparticle was discovered. And in 1995, CERN created the first atoms of antihydrogen. They made only 9 atoms. Today, CERN can make thousands in hours and millions over larger experiments. But even millions of atoms still weigh almost nothing. Question 1. Why do scientists have to create antimatter? Because we cannot simply mine useful amounts of it. At CERN, high-energy particles are smashed into a target. The collision creates many new particles, including tiny amounts of antimatter. This is basically mc2 working in reverse. Energy can become mass. Question 2. Why is antimatter so difficult to make? Because the process is incredibly inefficient. Scientists use huge machines and enormous amounts of energy, but only produce microscopic amounts. Even after decades of progress, we are nowhere near making a visible amount. Question 3. How much can we actually store? Very little. Scientists can trap tens of thousands of antihydrogen atoms at a time. Special traps can hold up to around 1 billion antiprotons. That sounds huge, but the actual mass is still unbelievably tiny. Question 4. What happens when matter and antimatter meet? They annihilate. From a quantum point of view, they are like matching opposites. When they meet, the original particles disappear and their mass becomes energy, usually as very energetic radiation and other particles. So simply, matter plus antimatter, energy. Question 5. How can we store something that destroys itself when it touches matter? We cannot put antimatter inside a normal bottle. If it touches the wall, it annihilates. So scientists use an almost perfect vacuum and powerful electric and magnetic fields to keep it floating away from normal matter. In simple terms, the magnetic field becomes the container. Question 6. Then why are scientists still interested in antimatter? Because its future may be space travel. If we eventually learn to make and store it efficiently, tiny amounts could provide enormous energy. Spacecraft could travel much faster. Trips to Mars could become shorter, and missions to Jupiter, Saturn, and beyond could become much easier. Question 7. Is antimatter better than nuclear fusion? In terms of energy packed into a tiny amount of mass, antimatter is more powerful, but fusion is much more practical. Fusion fuels such as deuterium can come from water. Antimatter must be manufactured, is extremely difficult to store, and produces intense radiation. So fusion is far more likely to power our cities first. Antimatter may have a different role. Fusion could power civilization on Earth, while antimatter could someday help civilization travel much deeper into space. And here is the amazing part. We have gone from only 9 anti-hydrogen atoms in 1995 to millions today. But the amount we can actually hold is still microscopic. So antimatter is real. The real question is whether humanity will ever learn to make enough of it to change our future.